Okay, so welcome everyone to this session of the Circular Industries talks. And we have today with us Rogier Nijssen. He is a lector composites at the Hogeschool InHolland, so the University of Applied Sciences in. And he will be presenting his work on composite materials. Composite materials are, of course, very crucial for the energy transition. Just look at, for example, wind turbine blades. And at the same time, they can also be a bit problematic in terms of recycling. So I'm really happy that that Rogier wanted to join us today. So without further ado, I would like to give you the floor, Rogier.
Yeah, thanks a lot. I'll try to properly share my screen. And maybe the presentation is more interesting than my inbox. I'll get started. I cannot see the chat at the moment, or if people are entering, so I hope somebody will interrupt me if something relevant happens there. Yeah. I expect to take about 25 minutes as kind of planned. If there's anything unclear or if you have something very intelligent to share, in the meantime, please don't hesitate to interrupt. I think we have an hour in total, so that should be plenty of time. So thanks a lot, René and colleagues, for this opportunity to present about opportunities. I have this presentation already with contributions also from my colleagues Twan, Bronja, and Mark. My name is Rogier. I'm a professor of applied sciences at InHolland University of Applied Sciences. I'll talk a little bit about what we've been doing with composites, because it's also kind of relevant for our current endeavors. But I would say the main focus of what I want to share today is our current activities in looking at mycelium as a structural material. Some black and white pictures from the past. So I've been working with this University of Applied Sciences for about 12, 13 years. And initial focus was on composite materials, so fiber reinforced plastics. And we've done, as is kind of usual at the Hogeschool, applied research projects, where we're working in general on themes that are maybe not very new in general, or fundamentally new, but new for several fields. I'll explain it in a bit. But one of the examples, I guess, is composite materials. We have other themes as well where we do applied research at universities. But composite materials are not new in themselves. They're well known in aerospace aeronautical engineering. But to translate them to applications for civil engineering or building or architecture, that takes some effort. And that's where I think our strength lies. We've done that in different ways. So I mentioned already the applied research projects, very often in the framework of a RAAC subsidy, where you can work together with other universities of applied sciences and also small, medium enterprises. Our focus has been in these projects a lot on automating manufacturing. That already touches a little bit on improving sustainability of composites in general, because, I mean, the composites themselves, there would be glass fiber, carbon fiber, and fossil-based resins, so dirty in themselves. But by exploring automation options, mainly focusing on vacuum infusion process, we hoped that we would help enable the transition from open mold hand lamination techniques, which were still very often used in small medium enterprises, to closed mold vacuum infusion. And it will be more closed mold, so less emissions, for instance, of volatile organic content, but also better quality, higher strength materials, so lighter weight structures and hence less energy intensive, so to speak. Actually, yeah, all right. So those are the top pictures that refer to that. It's always a collaboration, so a lot of people in there. We also worked in the theme of bio-based composite materials, very much focusing on the fibers and the strength, the structural properties. One of our first projects, it's the middle picture in the slide, was on a bio-based scooter frame, electrical scooter, made out of flax and hemp. But we also contributed in a project led by Avans Hogeschool on a bio-based bridge. And this was the first Here's a small picture of that first bio-based foot and cyclist, a pedestrian and cyclist bridge in the world. Almost 100% bio-based, except for the nuts and bolts that were still in there. It was already mentioned in the preliminaries to this meeting, but whenever you watch the presentation given by me, there's going to be something with wind turbine blades in it, because that's kind of my hobby horse. So there's a picture in here from the AirTub program. This is going to be a sequence of various multi-year projects. We just finished one, and we hope to start the next one, so stay tuned for that. And that's aimed at reducing, minimizing to zero maintenance with people of wind turbines and wind turbine blades. So what you see there is a drone that's going to inspect wind turbine rotor blade, and later on there would be another drone developed, for instance, by our students that would land on a blade and repair it. For instance, leading edge erosion, rain erosion damage is something that could be repaired in this way, and therefore you would prolong the life of the blade and make your composite more sustainable. We work together a lot with the industry association, Composites NL, and also a way of furthering, let's say, the knowledge on composites in this field and the applications is, of course, done through education. So we've made books, but also, let's say, educating the industry by contributing to design rules and design guidelines. So that's a couple of, let's say, activities and themes that we've been doing throughout the years, and they're still relevant, I would say, for our current activities. So that's why I'm dwelling on them a little bit. We've shifted our focus a little bit, and we broadened it, if you will. So composites, it's a very straightforward topic, but I mean, in this day and age, there are more urgent societal challenges to work on, and of course, energy and materials transition is two of them. It's very broad and very also deep topic, but I think it can be summarized in two words, namely ban fossil. So what we want to do in our work, what our mission is here, is to take out all the fossil sources in our energy and materials production, and it's still kind of a challenge. I'm not going to talk too much about the energy transition part and ambitions that we have today, but I'm very open to discuss those with you after this meeting, for instance. I'm going to focus a little bit on the materials transition, although we are aware, of course, that those two are very much coupled. So the hobby horse example in this frame would be the wind turbine blades. I mean, 20 years ago, we thought we were doing a really good job in building bigger and bigger wind turbine blades that could last for hundreds of millions of fatigue cycles in 20, 25 years. But we didn't want to think, I guess, too much about what materials we put in there and how we could or could not recycle those blades. So we're doing that right now. That's a little bit too late. So what we're trying to do is stay aware of this coupling and make sure that whenever we're working on new materials, also think about energy that's involved and vice versa. So the way we do that is we try to make our students and colleagues very much aware that the product has a design, not only a design life, but it has a whole cycle, and there's a life after the use of the product. And of course, it's quite obvious, but it's not that much ingrained in everyday design practice yet, as it should be. So we're teaching them life cycle analysis, making them aware of integral design methods and all that stuff. And right now we have a bunch of projects centered around mycelium. I'll get to that in a minute. What I also want to mention is, and that's again, let's say, a coupling between energy and materials transition. We're going to start a fairly, in my view, exciting trajectory in the next year. It's called professional doctorate. That's a not yet formally existing academic title, kind of comparable to a PhD at universities of applied sciences. It's going to be developed in a pilot that's going to run for about 8 to 10 years. And our first candidate is going to start in January. Her name is Jasmijn Rijtrock, and she's going to work on chemical recycling of thermoset composites, kind of trying to help, for instance, the problems that we have recycling wind turbine blades at this moment. I'll get back to that at the end of the presentation briefly, if I still have time. So let's get to the point. For those of you who are not familiar with the concept of mycelium, mycelium in Dutch it's zwamvlok. It's the kind of the root system of fungus. So it's the thing that grows inside a dead tree or underneath the soil, and that in the end produces the visible mushrooms. There's a whole range of types and races, of course. What we're interested in the underground network, mycelium network. And when you look at that through your eyelashes, you can grow it, for instance, on a woody substrate, such as hemp fibers or flax fibers or wood fibers. And when you complete that growth process, you end up with something that through your eyelashes looks like plastic foam. For instance, polystyrene. It's even white or whitish. And so obviously we're looking at applications of this material in thermal or acoustic insulation, but you could also use it as core material in composite sandwich structures. So we're also definitely looking at that. There's really a lot of knowledge on growing mycelium, but it's mostly based on mushroom cultivation. So people are not that interested in mechanical properties of mycelium, but we are actually focusing on that. What's really nice about this material, there's also a lot of disclaimers and things we need to work on, but what's really nice is that we think it can be a fully circular material and that you can manufacture it with essentially no fossil fuel sources. There is, of course, a lot of energy involved in making mycelium because, first of all, you have to sterilize your feedstock, and that's kind of at a high temperature. Then you keep your material at an elevated temperature for a couple of days or maybe even a couple of weeks to grow the mycelium, to colonize fully the substrate. And then you have to stop the growth by, again, elevating the temperature. So there's a lot of temperature involved, but it's, let's say, low quality, low temperature environment that you need, so it shouldn't be too challenging to use renewable energy for that. You can use local waste to make the material, so that's also an interesting way to add value. In the end, we're also interested in the business case, of course. Here's a couple of, it's kind of a multifaceted material. Here's a couple of examples. So if you grow it inside a fibrous substrate, you get a block like you see at the lower left corner. I hope my slides are not mirrored in the presentation. So over here you see a block that looks kind of like a polystyrene block, but it's a block of mycelium, fully circular. Next to that is a mycelium only, so there's no substrate in that. What you end up with is kind of like a soft cushion-like material. First thing you think about is you use that in upholstery. What you can also do is compress, maybe with a little bit of heat, your grown mycelium into a panel, and that kind of is reminiscent of a building panel. You can do it at different stages. This one is not fruited. This was already a little bit fruited, and at the top right corner there's a sheet of myco leather. So mycelium can also be processed into something that looks a lot like leather. And if you go to the shop and you buy shoes or purses that are made of vegan leather, it's very often mycelium material. So different phases, same material, and it's also quite promising, I think. So in our preliminary research that we've done in previous projects, we look at different applications. At the lower right corner, there's an aircraft interior divider. It's development by Airbus that we worked with, and they had a very innovative dividing panel made with 3D metal printed trusses, and it's hard to implement a standard core material in there. But we used mycelium as a core material that you could grow inside such a complex geometry. And that's also one of the things that we think is interesting about this type of material, because when you think in terms of manufacturing methods, of course, there's the old-fashioned machining. So you take a block and you chip away, and then you end up with your product. Additive manufacturing is a bit newer, so 3D printing and composite materials. But this is a growing material. I'm not sure if there's a term for that, but you could call it a crescent or incremental manufacturing method. And it will, in my opinion, give a lot of new design opportunities as well. So from a design philosophical point, it's so quite interesting material. We looked at wind turbine rotor blades, of course, and specifically at the sandwich panels that maintain the aerodynamic shape and usually contain balsa wood or PVC foams. And we looked at, could we use mycelium for that to have less environmental impact in these blades and make them also more easily recyclable later on. What you find out in those projects and also in the surfboard project that you see in the lower left corner is that sometimes it's not actually 100% clear what is the minimum demands to a certain material property that you need for application like that. So translation or essentially when you look at mechanical properties and you see that they're not as good, very often they're not as good as artificial materials, it's not always obvious that that will be a problem. We did do already a bunch of preliminary mechanical tests on mycelium, so essentially loading and breaking it in almost every thinkable direction. In general, I would say mechanical properties, if you're used to artificial fibers and plastics, they were a little bit disappointing, but I already mentioned the caveat that you don't always need high properties. And there is some interesting concepts there as well. So one of the things we did was make a mycelium kind of a sandwich block with two different types of skin. And one skin would be a flex fiber, woven flex fiber sheet. And for other specimens, we used woven carbon fiber sheets. And then we grew the mycelium. And the nice thing is mycelium will grow in between the openings between in the weave and attach itself to the skin. And the interesting part about that is that you might be able to skip a gluing operation in making a sandwich structure, for instance. And the other thing that happens is that mycelium really connects to the flex fiber skin because it partly eats it. And that results in at least a better, I wouldn't say good, but a better connection to the skin than, for instance, with carbon fibers, which are not edible for the mycelium. So in the very small graph that you see in the lower left corner, and I just printed it small because it didn't have room, and also because the numbers are not that high, impressive, or interesting, but you see a bunch of lines here, if you put on your glasses, related to the carbon fiber peel strength. And then when I overlay that with the flex fiber peel strength, you do see, looking a little bit through all the spread in data, that a flex fiber is better connected to carbon. So carbon flex better. I do have a little movie because we're always trying to do a little bit of theoretical work, but then also put it into practice. I hope everybody can see it. I'm not playing the full movie, but it will be in the presentation, so you can look at the start, which has a lot of manufacturing in there. I just wanted to show surf dudes surfing on a surfboard. So this is a movie of manufacturing and testing of a fully bio-based surfboard. All right. So the message here also, I mean, this is the student that actually designed and built the surfboard and did the mechanical tests, or part of the mechanical tests to make sure that it would be possible up front. And I think it's always nice to make that link between kind of theory and practice. Currently, we're looking at mycelium mostly as a thermal insulator, as a preliminary for more structural work in the building sector. The idea is, let's say the overarching idea is that we have a lot of crises. There's an agricultural crisis where there's a, as you know, problem with nitrogen, and there's a building crisis. We just don't have enough buildings, but also no room to build. So using bio-based materials could be a part of the solution where you have, let's say, one solution for two simultaneous problems. You grow stuff, especially for building. One of the options is to do that in facade panels or insulation panels, or maybe a combination of those. So what we're trying to do right now with our students is to check out different recipes to grow mycelium, and then test them in the sense of how well do they conduct heat. And in future work, we will, of course, also look at other performance indicators, such as how do they respond to moisture and rot. Maybe anecdotally, it's interesting, the surfboard you just saw, it actually surfed. That meant a little bit of water came in. And we do see that apart from the white fungus that's in there, a little bit of green fungus is also developing. So the long-term behavior of these materials is going to be quite a challenge and interesting. But there's also a lot of bio-based coatings that might provide solutions. So working on that, I have a little bit of data here. Not going through that in detail, but I guess this is recorded, so you can always look at it slower and later. So in this table, you see the measurements we did in the device on the right, a conductivity setup, testing setup. And you see that the mycelium samples are actually pretty poor performance in terms of thermal conductivity. So higher conductivity is worse insulation. So poor performance relative, for instance, to the artificial materials at the bottom, and also relatively heavy. So at first glance, you would say this is useless, just use polystyrene. You cannot compete with that, and it's probably also cheaper. We really like to take up the challenge and create insulation panels, and there's already a little bit of work done in the industry, but we also have our own ideas of creating insulation panels and mycelium panels that can be used in structural applications that are maybe not cheaper in the sense of euros, but we also want to teach our environment and our students not only to think in euros. It's a good starting point because you cannot really start without them, but at the end you also need to look at long-term environmental impacts and price that in a sense. And then we think mycelium could be actually a good option, but it's going to be a challenge. One of the answers that we foresee to help answer this challenge is automation of manufacturing. Currently, a lot of mycelium products are made kind of in a batch-wise manner with single molds. The advantage is that you can have complex shapes and you can have different recipes really quickly. What we are going to try and develop is a, let's say, semi-continuous process in first instance manufacturing. And this is an artist's impression of a machine showing the input of spores and the output of a flat panel. So that's the first ambition that we have, make in a continuous process a flat, for instance, insulation panel. But of course, we are really interested in also turning that into curved panels or sandwich panels or things like that. Automation has all kinds of advantages in terms of productivity, but also in terms of certification, documentation of the material properties, because that's quite important also in the building industry that you use materials that are certified. Also, we think that by doing this, you can make smart use of the energy in the different phases and also save energy in manufacturing. First student project has already been launched. This is, if you can read the very fine print, first prototype by Thomas Jongejans of a he's a mechanical engineering student, of a sterilization and mixing unit for the feedstock. So one of the first stages in the process that we foresee. So stay tuned. We also did an interesting small experiment with computer vision, where we thought, okay, when you look at this mycelium in different growth stages, it just started and this is almost fully grown. You obviously see that it will turn white after a while. You can use computer vision to count white pixels or to quantify the whiteness of the material, and you can create graphs, something like this, where you see that as the substrate is colonized by the mycelium, your number of white pixels increases. Then there's kind of a plateau, and at a certain point, that's the second stripe over there, at a certain point you see that the mycelium is quite satisfied with colonizing the feedstock material and starts to fruit mushrooms. And when that happens, it starts to get brown again. So you will see a decrease in your number of white pixels. Now, this information allegedly can be used to predict what is the optimal moment for stopping the growth by heating the mycelium. And we also think that this could be an important part of the automation process. And also, since you're using a computer and you're documenting everything, this will be useful input for a certificate of your material, for instance. So that's so much for the mycelium. I just wanted to do a small shout out to everybody who liked this presentation and saw things that were interesting, or saw things that were interesting and not touched upon. So please, stay in touch. And we're always interested in doing applied research projects with you, so feel free to do that. And also, I mentioned already at the beginning, we're working on a professional doctorate, a pilot to develop the actual professional doctorate with guinea pig candidates, so to say. I'm really interested in talking to not only young professionals, but also people who've been in the field and have ideas on how to improve it. And see if we can develop more professional doctors. They are done in thematic clusters. I'm mostly in the cluster on energy and sustainability, so very much related to this this talk. And I'm interested in speaking especially with people who have tiny egos, because when you do this project, you're not guaranteed to get the formal title, because that's going to be anchored in the law during the pilot. So it's not a guarantee that you do the work and get the formal title. So you shouldn't be too interested in that. And it's going to be more work than a PhD, because it's going to be the PhD plus all the reflection on the process and all that stuff. So if you're not scared by and running away by this very poor commercial pitch, then please contact me and see if we can develop something together. Okay, with that, I'd